Hello, this time I'm going to talk about AdaBoost. AdaBoost is a method of a family of methods called boosting methods, in which the main idea is to generate many classifiers that are not very good by themselves, but when you put all of them together, you can create a stronger classifier. And AdaBoost is one of the most famous boosting methods. So let's talk first about the concept of boosting. Boosting, as I said, refers to a general, probably effective method of producing a very accurate classifier by combining rough and moderately inaccurate rules of thumb. So the idea is that we are going to generate many classifiers that are not very accurate. And that is why we call these classifiers weak classifiers. And they are, like it says here, rules of thumb. So most of the time these classifiers are very simple rules. So to begin, we define an algorithm for finding these rules of thumb, which are called weak learners or weak classifiers. And the boosting algorithm repeatedly calls this weak learner, but each time this weak learner is executed, will be fed with a different distribution over the training data. So this different distribution will be simply a different weight that will be assigned to each of the training examples. So every time you call this function that will train a weak learner or a weak classifier, you will provide this weak classifier algorithm with the same data set, but with a different vector of weights, saying which data example is more important than others. When we program an algorithm that is able to adapt these weights by itself, then we are talking about an adaptive boosting algorithm. The first algorithm that did this kind of self-adaptation was called AdaBoost. So each call generates a weak classifier, and we have to combine all these into a single strong classifier. Okay, and we do this with the hope that this strong classifier will be much more accurate than each of our single weak learners. So let's see an example. Suppose that we are given this data set with 10 examples. So we have here 5 positive examples and 5 negative examples. So these points are defined in a 2D space, so they are in this plane. Okay, and we start with some initial distribution, which is this D1 in our first iteration, so iteration 1. And this distribution is going to tell us the importance of each of the 10 points that we have for training. So initially we don't have any information, so all of these 10 examples will have the same importance, the same weight. So suppose that our first rule is to say, let's define a vertical line here, which I'm calling H1, This is going to be our first classifier, our first weak learner. I'm calling this H1, and we say our rule is going to be, okay, everything that is to the left of this vertical line is going to be positive. Okay, so these 2 points will be correctly classified, and everything to the right of H1 is going to be a negative example. So our 5 negative examples will be correctly classified by this hypothesis for this first weak learner. Okay, but we will have 3 misclassifications. These 3 examples are positive, but our rule is telling us that they are going to be classified as negative. So we have 3 mistakes here, and this error of classifier 1 will be this epsilon 1, and here we're saying that the error is 0.3. 0.3 because we have 10 examples, and the weight of each of the examples is going to be 0.1, because we need this distribution of the weights to be 1 if you sum the distribution or the weights of every one of the examples. So we have 10 examples. Initially all of them have the same weight, so the only way to get that is to assign 0.1 to each of the 10 examples. So since we have 3 mistakes, 0.1 plus 0.1 plus 0.1, that's going to be 0.3. So that's the error of our first weak learner, which is this vertical line. Now, in the same way that we will assign an error to each of our weak learners, we are also going to assign some alpha parameter to each of our weak learners. This alpha is a confidence parameter. So if we have weak learners that have small errors, we can trust them more, so they will have larger alphas. If we have weak learners that have large error, then we will have, or we will assign a small alpha, so we trust them less. Okay, so epsilon, once we have calculated epsilon, the alpha, you will see later that we would have a formula to calculate alpha as a function of epsilon, and this is going to be inverse proportional to epsilon. So at this point we have already generated our first hypothesis, our first weak learner. We have calculated the epsilon of that weak learner. We have also calculated the corresponding alpha. Now what we do is to change the distribution in the next iteration, iteration 2, and the way we are going to do it is we will increase the importance to those examples that were misclassified by our previous weak learner. So in that way we are telling our algorithm, you know, I want you to focus more on these examples because the previous weak learner could not classify them correctly, and I want you to focus more on this, to learn how to classify them correctly. So we increase the weight of those examples. So in this drawing you see it by just drawing these examples to be larger than previously, and the other examples we are going to reduce the importance of them, and here these appear smaller. So suppose that in the second iteration with our distribution 2 of weights, we make this hypothesis 2, which is our second weak classifier, and we say, okay, everything to the left is going to be positive, everything to the right is going to be negative. In this case, we have 3 mistakes, 3 misclassifications. We compute the error. Now it is not that easy to see where this 0.21 comes from, but what we are saying here is that each of these examples that were misclassified had, at that moment in the second iteration, they had a weight of 0.07, and that's why we are having here 0.21. Once we have computed the epsilon, we compute the alpha. Later on, we will see the formula for computing the alpha. At this point, just remember that if epsilon is small, alpha is going to be big, or vice versa. So we continue, we update the distribution. Now for the third iteration, since these were misclassified, we will increase the importance of them, and suppose that our third weak classifier is a horizontal line like this, saying everything that is above this line is going to be positive, everything below is going to be negative. We have some mistakes, we compute the epsilon, the alpha, and so on. So assume that we finish generating these weak classifiers, and that for us it is enough to generate only 3. This is of course an example. In problems that are not trivial, you will need to generate at least hundreds of these weak classifiers. But in this problem, suppose that we need only 3 weak classifiers. We need to construct now our strong classifier as a combination of all these 3. So graphically it would look something like this. We will say, okay, the alpha of the first classifier is 0.42, the alpha of the second classifier is 0.65, and the alpha of the last and third classifier is 0.92. So these are the alphas. Remember, they are telling you how much you can trust each of the classifiers. So all those classifiers with large alphas means that they have or they are making less mistakes at the moment that you classify points. So the final strong classifier, this capital H, will be computed as the sign of the sum of the opinion of each of the classifiers weighted by the corresponding alpha. Okay, so if you compute this expression and then you just simply look at the sign, if it is a negative number, then the strong classifier will give as final output and that this example is a negative example. If it is positive, then the answer will be that the point that you are evaluating is a positive example. So graphically, the idea would be something like this. Like if you put together all these 3 classifiers, you will be able to separate positive and negative examples. So to be more specific about how you implement this, let's consider a set of examples. In this case, we are considering pairs of inputs and outputs of m examples. So I goes from 1 to m. We have m of these pairs. Here we are assuming that x, the inputs, are vectors of dimension d of real numbers, and we are assuming that the labels could be -1 or +1. In the same way that in support vector machines we use the labels to be -1 and +1, also here in boosting and AdaBoost, it is important to use these labels. So for the algorithm that we are going to see here, you need to use -1 for negative examples instead of 0, like in logistic regression. It is important here to keep this -1 and +1. So we are considering m examples, where this x represent a features vector of an image patch. We are going to study this, or this example is going to be applied to images. Okay, so that's why here I am considering that this vector x will contain features taken or processed from images. And y is whether the image is a face or not a face. So this example will be about detecting faces on images. Okay. First, we need to define a distribution D over the dataset D, such that if you sum all of the weights of the examples, the sum should give you 1. That's why we are saying that it is a distribution. Okay. So to each of these m examples, you will assign some weight in such a way that if you sum all the D evaluations or the weights of these examples, the result should be 1. Okay, so a weak classifier can be defined as some function that will map vectors in dimension D to any of these two numbers, -1 or +1. A weak classifier must work better than chance. This means it has less than 50% error. If it would have higher than 50% error, just flip the sign. So what we're saying here is that our weak classifiers, this is a classifier, it's going to assign one of these two labels. They should be easy to compute, because you will need to compute this several times. And the only condition that we are asking is that the error is less than flipping a coin. So this should be less than 50%. So a weak classifier should have error less than 0.5. If it has an error larger than 0.5, we just need to flip the threshold, or here they're saying just flip the sign. Let me go back to the drawing. What they're saying is, okay, if your best weak classifier in iteration 1 has an error, suppose that the error is larger than 0.5, just flip the sign. So it means instead of considering positive blue in the left side, consider blue to the right side and red to the left side. So just flip the final decision. That's what they are saying. And if you get a weak classifier that has exactly 0.5 in the error, 50% of error, you need to reject this classifier, because it is not able to make a decision. It is not given any information in the process of classification. So you cannot accept this kind of weak learners. They need to be at least less than 0.5. So the error rate of a weak classifier ht of x, where this t here, this subindex t, will represent the iteration of the algorithm. So if you're talking about h4, we're talking about the weak classifier trained in iteration 4. Okay, so the error of any classifier will be calculated empirically over the training data. And this is the formula. Here this delta is just is going to have a value of 0 or 1 depending on this inequality here. So if your current weak classifier is predicting a label that is different to the original label of that example I, this delta is going to answer or evaluate to 1. Okay, so what we are going to do is to check every example whether they are correctly or incorrectly classified by our current weak learner. Every time these examples are misclassified or incorrectly classified, you're going to move your counter. You're going to sum 1 to your total count. Okay, so suppose that you have 1000 examples, m equals 1000, and 500 are misclassified by this HD. Then this sum will be 500 because you have practically counted how many were misclassified, and this 500 will be divided by 1000. So in the end you will have an error of 0.5. And here what we're saying is that you should make sure that this error is less than 0.5. In this example, if your error is 0.5, then this is not a good classifier. This is not a good weak classifier, so you need to try another one. Okay, you should make sure that the error is less than 0.5, and that's the way you compute the epsilon for every weak classifier.